First thing we'll observe is that we have high voltages at several of the buses in the system. Recall that the blue represents high, red is low, and green is within acceptable ranges. We'll start now and play the system in real time. First thing we'll observe is that there's high energy oscillations in this area, and we also have significant oscillations in the 0.75 Hertz mode and the 1.35 Hertz mode. First thing the operator will do is to take a look at what may have caused this event, and we'll replay the system from the start of the event. And we'll see that it starts out stable with no issues, and a few seconds into the system there's a significant drop in voltage. We'll pause the system now and figure out where these voltages are, and it looks like they're in Montana 1, Montana 2, and Montana 3. And we'll jump back now to the main page and continue the event, but we still observe that there's a very high angle difference between Northwest Washington and Montana. We'll start the system back in the playback mode, and we'll observe the event again, and we'll take a look at the frequency issues in the grid. So we'll jump to the frequency page and play the event in the frequency page. Now we'll accelerate the playback to double real-time speed, and we'll say this is where the event occurred. We'll pause and again take a look at what frequencies caused the oscillation. We'll see that Montana is the guilty party. We can actually hover the cursor over the value of the trace and get an idea of what the magnitudes of these systems are. This is the key thing that we're interested in. Montana 2, Montana 1, and Montana 3, you'll see that the maximum frequency was above 85. Minimum frequency was 35 for this disturbance. Now we'll take a look at the angle variations in this event, and again we'll play it at twice real-time speed so we can observe quickly the behavior of the system, and you see that there's no significant angle issues here, only small oscillations in the angles. We'll jump back now to the main page, and we'll take a look at the various modes in the system, and we'll put this in again twice real-time speed, and we'll see this is where the event occurred. A significant amount of energy was dissipated in this oscillation. The system returns to a normal oscillatory behavior for the first few seconds, but then the system is beginning to show a state of moving out of a stable equilibrium mode. Go back to the main page, and now what we'd like to do is take a detailed look at the shape of this particular oscillation. So we jump back to the main frequency page and use the zoom button to zoom out to the entire event, and we'll see this is where the event occurred initially over here, stable oscillations, and then an unstable oscillation occurs. And if we move the cursor over to the area, we can see the specific stations that were causing the oscillation. So Montana 1 had the largest oscillations. Montana 2 is shown here, and Montana 3 is shown here. We'll jump back now to the main screen. Now from the main screen we'll take a look at the actual oscillations that are occurring, and we'll jump into the oscillation page and start it at the beginning of the event. You can see initially there's an intense amount of energy dissipated in the first oscillation. This is shown by this large spike in frequency differences between Montana and Northeast Washington. Then the energy dissipates. However, now you'll observe that there's a peak appearing at 0.75 Hertz. The previous peak, as you recall, was at 0.9 hertz, so the system will automatically determine what the oscillations are, the magnitude of the oscillations, and it also shows the damping. So here we're at 2% damping, which is an unhealthy point to be in the grid. We can see that the damping is continuing to decrease, the amplitude of the oscillation is continuing to increase throughout this event. This is showing the frequency difference between Montana and Northeast Washington. This plot is showing the frequency difference between those 2 points and the angle difference between those 2 points, and you can clearly see the oscillatory behavior of the system between those 2 points. This plot shows the voltage versus angle, which also shows the intensity of the oscillation. The yellow dot indicates the current value, and the green dot is one previous, and then the rest of the trace shown behind. So you see we have oscillations also in frequency. Now we begin to see the buildup of oscillation energy at the 1.35 hertz. This is telling us that there's another mode in the grid, and now comes a second disturbance, and this 1.35 mode is emerging from the system and it's becoming significant. So the operator needs to make some aggressive action now to control the system to prevent it from going unstable. You will see the oscillatory behavior of the system now in the phase portrait chart, which is what these 3 charts are called. These are plots of the angle versus frequency or angle versus voltage. Now we observe that the system is continuing to grow in amplitude, and the operator, without an operator action, in just a few seconds the system will go unstable. Now we can see the intensity is dropping down, so that the operator action did have a positive effect. And we'll jump back to the main page now, and we'll take a look at the behavior of the system in the grid synchronization page. We'll go back to the grid detection page and take a quick look at the behavior of the system throughout this event. You'll see initially that there's been this large fault occurring in the system. It causes a large initial oscillation, which is immediately picked up by the move-in window FFT. The system looks initially to become stable. However, the oscillations reappear and start to propagate through the system. Now what we're showing in this chart is a plot of the intensity of the oscillation in the 0.75 hertz mode versus the intensity in the 1.35 hertz mode. We'll now increase the speed to 4 times normal speed so we can see the entire event. We'll see that oscillations are growing in intensity in both modes. And that's seen in this chart, but this is the 0.75 hertz mode. This is the 1.35 hertz mode intensity. This is the grid oscillation detection chart depiction of that event, and now you can see the system is returning to normal behavior. Now, just to summarize, what we saw is an event that had a duration of less than 2 minutes. The system had a fault in Montana, followed by a quiescent period, and then an unstable oscillation developing. Operator recognized this and solved it by adding generation to the system. Now we'd like to show a second view of this event, which is called a waterfall chart, and in the next you'll see a playback of that event.